Alright, let me bring you back together. Out of what you saw on the side here, which one of these are sparsely brought up? Which one of these you see every now and then, but they don't seem to pile on year after year and get worse. It's just every now and then it's a small problem. Which ones? Slow down, I can't hear everybody. So fractions, decimals is something that, it may not be the initial problem, but it's something that we can do interventions with. Tell me some other ones for intervention. You got it, word problems and schema-based problem solving. If you've ever gone through trainings on that, that's a great early start. Middle school, high school, the research is just coming around to middle school, not high school, and schema-based. But schema-based has some neat, that's an intervention design. Love it. Give me some other ones. All right, let's get to the big stuff. Core. Which one of these is a core problem? Bottom line is, you can't build an intervention if the core is not solid. You will not have success there. And so, place value, it starts early and starts piling on. If we saw factoring as an issue later on, that starts at place value. Let's keep going.
Vocabulary.
Vocabulary. Math is a language, right? Math is a separate language, and I think I made jokes about that when you saw me last. But if you don't treat math like a separate language, the child will not keep up with it. Okay, give me some other ones here. Multiplication. Why we wait till third grade? I don't know. Second grade is where it begins. Then you start tacking it on. In third grade, the mastery is set to be formed. But we don't even have 50% of our recent gen ed population hitting mastery by the end of third grade. And I say we, I'm not counting you in there, I'm counting me in the local districts when we do our assessments. In other words, what is called mastery in our local schools is actually not mastery according to an educational psychologist. 40 digits per minute, which is not the, it's got good research, but it's not the answer to every, I have kids who are slower processing. It is as soon as they can say the problem, the answer comes with it. That is not established early enough. And why is that a problem? Because if I have a 5-step problem, and I can't do computation, and I itemize it, right, and I find it's 5 steps, I just added 3 more steps to it. And if the child couldn't memorize his tables, most likely he's going to struggle with 5 steps as well. And you're now adding steps to kids with memory problems. So we've got to clean up and make it easier for later on. Love it. Give me at least one more. Interventions versus core.
Core would be like an integer number line number. Sure, yeah.
Number lines.
Yeah.
So, let's see, I brought my toy. Now, I didn't bring my big sucker, but I wanted to make sure that I showed what goes on. Wait, I got a light on, I think. If you haven't seen the new number lines, the new number lines go from -20 to 100, the kindergarten number lines. They are no longer from 0 to 100 in kindergarten. So all I do is bring in the sample pack that they do for when you open it up, and they're just showing you even on the samples we go to negatives. Why would they advertise to kindergarten teachers we touch negatives? Because,
Well, I was just, I'm sorry, I
So
can't
keep
talk. No, I was just thinking of, you know, if you did thermometers and stuff, it's below 0. We talk about below 0. And then again, your fractions and all of that that are below 1.
so we've got to make sure they understand the number line exists first. And don't forget, no longer are they selling just in the United States. We don't buy like we used to these manipulatives. This is international material, and if you deal with metric, most of the world wants your negatives early. So that's why what I showed you that last time, and I got the A's and the A's, and that's okay. That wasn't me. Welcome to India. That's where I stole that idea from. Welcome to China. Welcome to Sweden. Welcome to Finland. So what I'm getting at is be ready for the number lines to be changing, and we've got to start earlier. Even if you don't do the incorporation of the computation in there, they've got to understand addition goes one way, subtraction goes another. All right. And that's a single, again, one-dimensional mathematics. All right. So what I'm hoping that we walk away with this is to recognize some of these I can deal with as an intervention. Others, I have to team up with gen ed and make sure it's not a problem, because I see where the problem's coming. Now here's the good news about what we just did. Paul Riccomini, one of my buddies, has actually done research on this. And us teachers, we figure out error patterns very quickly. We actually don't need to do a diagnostic to figure out error patterns. We figure that out very quickly, which means what you have here in data probably is a good representation of Cabarrus, which sadly is probably a good representation of North Carolina, which sadly matches when I've gone to Alaska, when I've gone to Montana, when I do Ohio, Pennsylvania, Kansas, Florida, and in the state, it's the exact same conversation. In other words, we don't have a kid problem. I'm going to argue we don't have a teacher problem. We have a curriculum issue. Enough talking, old man, let's get moving. Okay, here we go. The only reason why I did this is to make sure that when you go back to the PowerPoint, you see what you said matches the national databases. So K2, these are the K2 issues that are coming out. The 3-5 issues, and long division is in there. And then 6 to 8. We don't really have good information on, when we do error pattern analysis, I'll show you the high school work. That high school work ends up being a repeat of everything you see. It becomes the ditto of that. And the data is not clear, so I left it alone. So here's what we're talking about. What is it in these progressions? What can I do early on that helps later? Well, you mentioned place value, so I want to focus on place value first as an example. So let's play a game. We're going to jump, there's on your tables, you have something that looks like a grid. It says array models on top. We're going to dive into the array model. I also put some base 10 blocks in there because I'm insane. So we're going to play with base 10 blocks just a little bit too. So I want to start the conversation. We're going to take a break, but I got to make sure I give you an example before that break. So you can play. All right. So take a look at this one. This comes from Karen Fuson. I'm not selling any textbooks here. I know we've had a conversation. Karen Fuson writes a series of textbooks. Sibylla Beckman's a mathematician in Georgia. They're buddies. We simply followed. I made it the same date, but we really followed their work. But take a look. 74 plus 28. It is not 74 plus 28. It is 7 tens, 4 ones, plus 2 tens, 8 ones. It is place value language. It's a kindergarten standard that is rarely pushed to the full extent. And so, what happens if I'm adding 7 tens plus 2 tens? The answer would be 9 tens. How about 4 ones plus 8 ones? The answer is 12 ones. What is 12 ones the same as? 1 ten, 2 ones. So what is 9 tens plus 1 10 plus 2 ones? You got it. I had 10 tens plus 2 ones, or 100 plus 2 ones. Now, if you're going to say, well, you know what, that sounds really odd to hear it that way. Well, somewhere along the way, arithmetic explains algebra. Mathematically, that's all it does. So somewhere along the way, a child's going to hear 2x plus 3x minus 5. And they're going to look at this expression, and they're going to be told to kind of simplify it or regroup within this expression. And what do we think they should automatically be able to do? 2x's minus 5, right? Oh gosh, nice spelling, nice counting there too. How about 5x's? Okay, that was the new math. Woo! Wow, big guy. My brain is obviously on the next example. Okay, so stop big guy. All right, so I have 20 plus 30 minus 5. And rather than calling this 20 plus 30 minus 5, I want the child to hear it as 2 tens plus 3 tens minus 5 ones. Which ones combine quicker? The tens. 2 tens plus 3 tens would be 5 tens minus 5. Where this looks like some algebraic thing with all these x's and it's crazy talk, it's only crazy talk if the conversation didn't lead them into it. It's called the arithmetic to algebra gap. Kids who do really well at the arithmetic procedure, but they don't do well with algebra. Why do we have such a gap? And this gap has been around since the 70s in research. In the United States and Canada, we have led the research on this gap. And what we found is that the way instruction happens at one grade level, if it doesn't progress to the next grade level, then I've got kids who have all these skills, they can do this, but they don't see a connection later on. So the hope is that if you really want a kid to get to that algebra, you explain the arithmetic procedure based on algebraic procedure. Make sense? All right, if we get really excited, we'll get into where determinants are actually the same idea. Where arithmetic is explained by algebra, algebra is explained by calculus. And so if you've ever stumbled yourself on calculus and said, I could never figure it out, you can probably go back and identify where the problem began. So what we need to do is try to label out what can we do to prep them on it. So ready to play? Let's get our turn. So I'm going to show you the progression of how this builds up, and then I'm going to ask that you guys get to try some with me. So take a look, instead of 74 times 28, 7 tens times 2 tens. It's an array pattern. This is the distributive property, right? So all this is the distributive property. So it's 7 tens times 2 tens. 7 times 2 is 14. 10 times 10 is 100. The answer? 1400. 4 ones times 2 tens. 4 times 2 is 8. Tens times ones is tens. The answer is 8 tens. That's that language piece now. 7 tens times 8 ones. 7 times 8 is 56. Tens times ones is tens. And I'll give you the teacher version in a second, but I need you to know math. What's happening? 4 ones times 8 ones. 4 times 8 is 32. Ones times ones is ones. Now, not every kid needs to hear all the ones and tens. They will get lost. So what we've come across in saying is 7 tens times 8 ones. 7 times 8 is 56. The answer is in tens. What we don't want them to do is say, look, there's 2 zeros, so the answer has 2 zeros at the back. Because welcome to decimals. It won't work. Because that'll be multiplying 5 hundredths times 25 thousandths. And then they're going to get confused of, is it the zeros after, or is it the ones before, right? Stop. That means that they're guessing what the answers are based on a procedure, not based on a concept. And procedures can be good if they're based on concepts. So here we go, next one. This one is odd, I know. And then what you do is you add all the products in here, and that's what gives you this answer. What happens when we're going? We all do this right in decimals. We've been told to do this right in decimals. But if your kids struggle on decimals and fractions or decimal fractions, that's where it comes from. The whole numbers weren't right. So 3 ones and 4 tenths. 2 ones and 8 tenths, right? 3 ones times 2 ones. 3 times 2 is 6. Ones times ones is, it's still in the ones place. 4 tenths times 2. 2 times 4 is 8. The answer is in tenths. 3 ones times 8 tenths. 3 times 8 is 24. The answer is in tenths, right? 24 tenths. And then 4 tenths times 8 tenths. 4 times 8 is 32. Tenths times tenths is hundredths. The answer is 32 hundredths. Make sense? We'll play an activity to make sure that language system fits us too. But look where this keeps going. Basic algebra. I don't think I go, oh good, I didn't pull it up. Here we go. So look at binomials here. 1x times 1x. 1 times 1 is 1. X times x is x squared. That's like saying 10 times 10 is 100. Tenths times tenths is hundredths. Now instead of saying tens or hundredths or tenths, I'm going to say x. It's a placeholder for something. It could be a placeholder for place value itself. 4 times 1x. 4 times 1 is 4. The answer is in x. Or 1 times x is x, right? You decide where your language goes. 1x times negative 3. 1 times negative 3 is negative 3. The answer is in x. And 4 ones times negative 3 ones. 4 times negative 3 is negative 12. The answer is in ones. Has anybody ever seen this pattern before, Big Belt?
We do it box method. Yeah. And
Same approach.
but we also, we use box method because we'll do the 4x4 to do it, but we'll also do a 9-square box so we can factoring. Yep.
Which is where you can take this,
Yes.
right?
Yep.
And by the way, if you're into quadratics, the factory now, you rewrite the quadratic inside. This is just to make sure the language for those who doze in and out with me, so you can reread what did Witzel say during that time. But because you would never make the kid write all that. Well, maybe you would. I wouldn't make the kid write all that. But I want to make sure that when they rewrite this through, that's where they pull out the factors from it. Now, there is a guess and check version of that before you introduce quadratic equation. But it's the same discussion. 2x squared times x squared. Sorry, this projector cuts it off. And so I would say 2x squared times 1x squared. 2 times 1 is 2. X squared times x squared is x to the 4th. Everybody, does it make sense? All right, what are some confusions over either the box method or an array pattern? All right, let's try it. Your turn. So grab that array, box it out for you. If you are not into whole numbers and decimals, you are going to do this in practice of the factoring. Practices with binomials, with polynomials. Have fun with it. I know, I'm the type that would. And while you do that, I'm going to do a pictorial version of it up here. Oh, sorry, working break. Thank you. Working break. We are now at 2:25. Let's get back here. Well, 2:30, depends on which one I'm going at. Wow. Okay. Let's follow that one, and we'll get back here at 2:40. Is that fair enough? Okay, so working break.
I have trouble staying awake, and I don't need food.
Oh, shoot. I was so close to emailing somebody saying, I'll pay you big money if you go all over and get me cheerleaders.
Oh, you should have. I would have done that for you. I'm right there at it.
I was so close on that. Okay, I'll wait.
I'm having that.
Y'all were supposed to be done.
So the OT came out, she's saying a lot of stuff for ideas she was saying she knew that they were thinking about bringing her back. And so she wanted only kind of wanted me to do activities at the counter or whatever.
Get some staff.
Yeah. She said that she was really interested in that.
She had back surgery. Or did she? There's so many fucking.
She's the one that has seizures. So yesterday, I just get out of Stephanie. So she's like,
This one, that and that mom, they called me and had my name done with me. If I was after school hours, I wanted to say something. Sorry, I can't make any promises. I tried so much. It was not working today. So I need to talk to them about how much of a behavior problem is one-on-one, but I'm thinking it's tough either way, so anyway. But thank you.
I'm talking to somebody else.
She was like the next week.
Yeah, that's what I thought. I was like, what?
She's
That's what I was afraid. Combine that together. She's down in right off the Union and some breath is turned out off the school and I mean there, which is all right there downtown.
So y'all were gonna.
That's why
Instead of saying 4, 5, 6, 3, 2, 10.
I'm going to plug up my computer. It's my first year.
Yeah, because that's what I just want to hear. Setting up the 10 but it's waiting for
all very, very small. So you're used to that when you're put in.
We'll give it a try.
We still feel like a really small school. This is kids who have like 1,000. That seems like that was Oh, yeah. I'm in treasure too. Yeah. You're not going to build that you need to build onto the building, not
Yeah, so it's kind of right in the middle of school. Yeah, well, it's weird. Yeah, it's like little like pause. Yeah, but it doesn't look like it, Joe. I mean,
It really doesn't look like her typing, and I can't figure it out. I really can't. Somebody typed it, and I was like, where are we at?
yeah, when I was like, I was like walking, I was like, I'm just great, so lost. But, I mean, now that.
All right, as we get back here, what'd you all get for your answers? 2 10s, 4 1s times 5 takes 3 1s. Is this kind of what you did? All right, now remember, when you practice this, you've got to practice. Okay, one of my friends is Kawana Dobbins. I didn't know what dirt poor was until she explained. I thought dirt poor was a cute expression. I didn't know it meant you grew up with dirt poor. I didn't. Kawana is actually a Department of Defense teacher. She teaches when she was in Guam. Now she's in Japan. But she's right when you grew up in South Carolina, you eventually say, I want to see the rest of the world. So she's been off in East Asia having a great time. But Kawana says the best way to memorize any of Brad's stuff, what she calls Brad's stuff, it's not my stuff, that's her world. She goes, talk to yourself. She goes, sit your dog in front of you and talk to your dog, because math is such a verbal profession. So you've got to make sure that you walk it all through, because it's not just, oh, I see how he does that. You're going to have to, how do I say it? It might sound quick off my tongue, because I've been doing it this way now for 20 years. But that doesn't mean that if you just started it, it'd be like, don't think that you have to do it the way I do it either. Some of my procedures I've cleaned up over time, because like one of my favorites, Abigail Armstrong, a middle school math teacher. So it takes a lot of my stuff and makes it kid usable. Rather than, she's the one who goes, use the X, instead of, 1 times X is X. And she's the one who says, no, use the X. And she's found ways to clean up this. So I appreciate that. All right, over here, same thing. We're used to this conversation. But how many times do you really go 0.3 times 0.4? And then you go, okay, well, it's 12, but does that mean the decimal goes 2 over? Or does it go in the middle? You're negotiating where the decimal moves. But if you say the terms, tenths times tenths, the answer will be hundredths. You got it, I know what you meant. But the answer is going to be hundredths, so it's 12 hundredths. And that challenges it. Now, the first time anybody ever said to you something like 1,500, I'm sure you were much younger and you went, they're talking about 1,500. That's because we were never taught place value. Our language system doesn't use place value. So we've got to start, now this is later on, but we've got to start early building place value. So, in case you've ever seen array models, if you're like me, you just want to play with toys, right? You can ignore Witzel for a little bit here, but don't forget you can set up an array pattern as far as modeling or box method, as far as modeling even up the polynomials with this, right? Like x plus 2 would be a long, short, short, times x plus 3 would be a long, short, short, short. You can even do negatives. Now, some of you have packs. It's just because we packed them on. You can have positives and negatives as well in there. Just make sure they're different colors. But you can go through and do polynomials, well, I think it's binomials, I think polynomials is a mess in the way, right? This is two-dimensional, not three. But this allows you at least to see it. So in other words, 4 and 3/10 times 2 and 4/10. 4 ones times 2 ones, the answer is 8 ones fits in perfectly. What's 2 ones times 3/10? 2 times 3 is 6. Ones times tenths is tenths. So it goes into a tenth of the size. Over here, 4 ones times 4/10. 4 times 4 is 16. The answer is in tenths. And 4/10 times 3/10. 4 times 3 is 12. Tenths times tenths, hundredths. So if you haven't seen these, and you're not going to make money, if you can find a better way to do this, please do. But instead of, please don't call this a flat. If you read the original instructions, they call this a flocks. Right? This is a long, and this is a units. Now the only reason why they use those is so they can describe to you within a couple pages, kindergarten versus 5th grade. But when I'm using this as 100, I don't call this anything but 100. When I'm using this to represent 100, I call it 100. When I'm using it to represent 1, I call it 1. The reasons why is if you get stuck ever with CRA and you go, it's not working, it isn't that CRA is not working, it's that you're using different language for different steps. The power of CRA is not the manipulative. The power of CRA as an approach is your language. So whatever language you use during the concrete steps is the exact same language you will want to use during the pictorial and the abstract as well. And in that, you'll be able to find a good CRA approach versus a bad one. So if you're buying these approaches, if you're the type of person that likes to buy those kind of kits, you can know which ones are good, which ones are not. Just thumb through it of which ones say the same language over and over again. All right, let's go off and play a bit. Oh, I do C, and if you do C, transition to R, right? Which is no longer size proportional. That's what pictorial representations are, no longer size proportional. And then make sure you